I want to make a robot, but I can't ever do anything the easy way. I always have to do things the hard way. And in particular, the one that I was the most excited about was a hexapod, a six-legged walking robot, although hopefully it'll fare better than this one did. Wheeled robots just seemed a little bit too simple. Walking robots are more interesting. Now, I've been watching a lot of other robotics YouTubers. I've noticed something interesting, that most of the walking robots use servos, which are very nice little devices, but unfortunately they limit the ability of the robot programmer to give the robot more sophisticated behaviors based on what its legs are doing. For example, if a leg gets stuck on something or one of the motors malfunctions or something along those lines, the robot has no idea, the controller has no idea what is wrong. The controller has no idea that anything is wrong. The robot just acts really dumb in response. And I feel like this might be a dead end for a lot of people getting into hobby robotics. That you pick a servo and you start building your robot and you start programming its gait and it limps or it does something weird and you don't know how to fix it other than just tweaking numbers until hopefully it works a little better. But it's not a realistic solution, and you also can't do anything terribly clever like reacting to terrain difficulties just because you don't have the information. Now, as a software engineer, I always want to fix this with more code, but unless I have more information, I can't really do anything useful with the code. So what I decided I wanted to do was something a little bit more fancy than servos. I wanted to use plain old, simple DC motors. This, for example, is a common TT motor, I think is what they call it. It's just a little hobby motor with a little gearbox on it. That's all it is. It's not a servo. It doesn't have position feedback. It runs continuously. Has pretty decent amount of torque, but there's still the problem of how do you control this from a microcontroller or a controller such as a Raspberry Pi or other small computer. Now, I did find some Arduino shields that could control these, and I found some Raspberry Pi hats that could control motors. But the most I was able to find is a hat that could control 2 motors at a time. And for a hexapod, I want it to be able to move left and right like this, which is really helpful for the walking gait. I want it to be able to bend the whole leg up and down like this. And I want it to be able to move the end of the leg, which this model won't do because it fused on the printer. But it needs to be able to move on the tip as well. That's 3 degrees of movement on each leg, which means 3 motors per each leg. 3 times 6 is 18. That means I instantly need 18 motors. I think 9 shields on an Arduino or 9 hats on a Raspberry Pi is going to look pretty ridiculous. Not to mention, I don't know if the shields or the hats are actually intended on stacking on each other. And if they are, I don't know if they're intended on sharing power between all of them, which would mean that you would need like 9 batteries for your robot. And it's just, at that point, it's just way ridiculous. Now, I'm aware that there are servos that have serial control. You can get them, but the problem is that from memory, they were around $60 each for these serial controlled servos. That's a lot of money for 18 servos. And I don't need them to be particularly large or complicated either. We're talking hobby robotics here, not professional robotics. So I set out to find a better way. If I needed to build a circuit myself, I would. It's not ideal. I'm a software engineer, and I'd prefer to just, have a simple computer like a Raspberry Pi and then plug a few motors into it and do the rest from there. But that's not the way that it was going to work out. So I started looking and researching ways to do this, and I came across a couple of little motor controller boards. They're usually basically a breakout board for a little H-bridge microcontroller or integrated circuit. The problem with these for me is that I really wanted to target a lower price point, and it was going to be around $8 to $10 for each one of these little H-bridge drivers, and they were only going to let me drive forward and backward, which meant that I wouldn't get any of the feedback I was hoping for. I decided I was going to need some potentiometers, so I got a whole pile of them. They're really cheap. Potentiometer, I'll talk about this more in a later video, but very simple thing, and it just has a knob that turns. These are a little bit stiff, so they might not be the best ones to use for the final product, but for the moment, this is what I'm going to play with because this is what I have. Now the idea is that I will have the motor and I will stick a potentiometer onto it and have a 3D printed enclosure for these that holds the potentiometer next to the motor, and then a little gear system will connect the two. Now that'll give me essentially the ability to do a servo for every one of the motors. But then I ran into another problem, which is that every one of these potentiometers needs an analog input on the microcontroller. 18 analog inputs is a lot. There are not very many products out there that I can find to buy that have that many analog pins. The Arduino Mega might have them, I don't remember, but that's a big board. And again, I don't even have any of the other feedback that I would like to have, like whether the motors are stalled or whether they have too much current flowing through them. So I started looking into how do I do current sensing, and yes, you can do current sensing on servos too, but that just complicates them. So I stumbled upon a brand new microchip from Texas Instruments that is designed to control DC motors with current sensing feedback and some other nice features like stall detection and fault detection, such as when you don't have a motor plugged in. And of course, since they're brand new, there are no breakout boards for them or any products for them yet. So I started thinking, how do I do this? And I thought maybe I need to make a PCB. I need to make my own breakout board for it. And lucky for me, there are some fantastic YouTube tutorials available for starting with KiCad, which is a free PCB design software, and designing my own. So I jumped in with both feet and started doing that. I have a little bit of electronics background, but no formal training or schooling. But I know enough to be dangerous, and I know how to read a data sheet, which is just documentation. So something I'm used to from software development. So I did, and now I have a PCB, which turned out to be quite a bit more than I was expecting. I'll go into this in a later video talking about what this is more in depth, but a quick overview. My thought was economies of scale. If I only have to buy 3 boards, then the markup on 3 boards would probably be less than a markup on 18 boards. So each one of these drives 6 motors. Each one of these has a lot of analog inputs. It has one analog input from the motor driver itself, which tells how much current it's sending. And then you can plug your own analog inputs into it. So one of them would be useful for a potentiometer. Another one could be useful for a force sensor, or a light sensor or some kind of a touch sensor. There's lots of things that this could do. But the point is that there's enough for 2 of those sensors per motor that you plug into this. And a whole bunch of additional GPIO pins for whatever you want, and I2C or SPI for connecting to other whatevers. So this board then becomes powerful enough that you can use it to be the only thing that controls a robot. You can use, it has an STM32 microcontroller on there, so you can easily program it with Arduino or Rust. Anyway, I went a little overboard with the design on this. I'm still trying to test if I actually did the design correct, which is why you only see a few of these components on here. I'm currently working on that, but more to come on that one. So I'm working on the 3D modeling for this robot. I actually did buy a whole 18 servos. I have a whole 18 servos. This is only a third of them. So I'm going to be building a regular hexapod out of servos, the way that a typical hobbyist might do, mainly to showcase the differences between what it is like to build with a servo versus using another hobby motor. I also have these slightly higher speed TT motors, in addition to blue motors, which are very similar, except that this one uses metal gears and has double the torque, so half the speed. Now, if I'm wanting to make a big, strong, heavy robot, I'd probably go with these. This one will probably be a little bit more nimble, but we'll find out how it performs as we go along. I also have another tiny breakout board for a slightly different version of the motor controller chip. This one's even smarter than the one in this one, because each motor chip can be controlled over I2C, which means that you only need 2 pins to control almost as many of these as you want. There's a little bit of a limitation, but you can control, I think it's 9 of these with just the 2 I2C pins. So that's about what I've got for this video. To give you some idea of what's coming next, by the time you're watching this, they may already be out, so go ahead and look for links. I'll post them in the description. In my next few videos, I'm going to be exploring this board. I'll talk about what it does, what the different parts of it are, whether it works or not. I'm fully expecting that since this is the first one I've done, this one won't work. So we'll talk about maybe some of the mistakes that I've made there. Then, because I don't want to wait 2 weeks for a new version of these, just to find out that those are also broken, I decided that it would be fun to experiment with making my own prototype PCBs. So that's the machine you see next to me. It's a cheap CNC router with surprisingly good low run out and good precision. So I have a pile of interesting things sitting next to me for prototyping PCBs, which I will be going into the process of learning how to do that. And just so you're aware, this is a 4-layer board. I don't know very many people that do 4-layer prototypes at home. I can't find any videos on how to do it, so stay tuned for that one. I might fail completely at making those, but at least you'll get to see whether it's worth it or not. I also have, I don't remember the exact bill of materials. There's probably over 100 components, and they're all 0603. And the smallest of which are 0603, which are 1 millimeter by 0.5 millimeter. They're tiny. They're small enough that you sneeze while you're holding them in tweezers and it disappears forever. I've had that happen a couple of times. I don't want to put all of the components on these all the time. So I also have parts and designs in progress for a pick and place machine. So subscribe if you want to see the progress. So if you like robotics, electronics, programming, or any combination of the three, then subscribe to be notified when the next video is out. Also, feel free to let me know in the comments anything that you want to see. I will be programming in Rust for most of the board, and I plan for all of the software to be open source. Also, let me know in the comments if these projects sound intriguing to you, or if I've missed anything that would be that you're curious about. I intend for these to be priced at a point that is very friendly to the hobby market. So if you want to get your hands on these or help me with developing or testing them, definitely let me know in the comments. And thanks for watching.